Hey, good afternoon, guys.
Hi, how are you?
I'm good. How are you?
I'm good. Yeah.
Excellent.
Today we will continue and we are starting from the compiler concept and design. Okay. So why this need to be a separate part? Because this will be a starting point for the whole chapter 2, 3, 4, or even 5. Okay. So this whole part is a unit, big unit. It's talking about compilation, okay, or interpretation. You can talk about it in different way, interpretation. So let's get started, okay. So first things like theory, okay, automata theory and background theory. We talk about the combinational logic, finite state machine, push down automata, and Turing machine, okay. So let's go back to that portion. Okay, last time we probably talked about it a little bit, but I actually may skip something in the middle. So let me see. Right here. We talk about combinational logic, right? And then we put some memory for feedback, right? And then the next thing, okay, we cover this neural network, whatever stuff, okay? And now we are going to, here, we are going to go back to look at this theory portion, okay? So combinational logic is input, output, garbage in, garbage out design. So you basically have a few bits coming in, right? N bit coming in, M bit coming out. That's your machine combinational logic. And then we have finite state machine. You have input, you have finite state machine, FSM, and you have feedback, you have memory, and then you come here and that's your machine. With that, you have states. Okay, you have states. And that's not enough. Next one is push down automata. So we have finite state machine over here. Here, the finite state machine logic actually is the same with this logic, combinational logic. Still, n bit in, n bit out. You still have a memory. And then push down automata, add one more thing, you have stack. You guys know stack, right? S-T-A-C-K.
Yeah.
Stack. So
Yeah,
it's a push and pop thing, right?
Right. Yeah.
Yeah, and adding that, why is important about adding the push down automata? Because you start to be able to operate recursion, right? Recursive recursion, and you can have the function call, right? And here, finite state machine, you basically go state by state by state and go to certain state and then come back to certain state. So it actually more like structural computing, programming, okay? And well, these three, whatever you can spread by this guy can all be done by this guy, can all be done by this guy. So actually, they are almost like equivalent, okay? Almost like equivalent. So the next one is the universal machine model. You have a same logic. You have you have the memory. You have push down automata. You actually also have a tape, okay? They took out a tape, so you can move the reading head back and forth, something like that. Okay, that's universal Turing machine model. Okay, so they claim that whatever can be done by any computer, Turing machine can all do it, right? You guys may hear about that, right? But that is a paper machine, and the assumption is like, well, there's assumption is that memory is infinite, right? So you actually assuming that the machine is super big. So that actually means that if you have some computation and given enough memory and given enough time, whatever computer can do, Turing machine can all do it. So that is humanly possible by doing Turing machine. Is that okay? And that's the limit that current computer can do, okay? But something Turing machine cannot do will be, say, analog circuits, right? Some analog circuits actually Turing machine cannot do, okay? and also neural network. Okay. And you may claim, you may ask me that, okay, how comes the neural network actually, right now, you look at the iPhone A12, they have Bionic, right? And it's in processor format and digital. So whatever I say actually should be able to be done by Turing machine, right? Yes, that's true. Whatever currently doable by the human design processor, Turing machine, the paper machine, should all be able to do it. Yes, that's true. But neural network actually right now have different model. If you look at traditionally neural network, is that you have a neuron, right? And you have synapse, right? So you connect into different location, and nearby you have different neuron, and then they pass information to each other to do computation. So each one of these actually is not digital. It actually has some sort of integrator, or we call it capacitor, or okay, and then they do some sort of optimization over here. So the things like why neural network sometimes can do but Turing machine cannot do is like you may have an optimization problem, right? So by Newton's gradient descent method, you may only do some sort of optimization and find the local minimum here, right? So global minimum here, if you starting from here, maybe you are not able to jump over the here to do this. So they invented the annealing algorithm, software annealing, hardware annealing, and so you actually given some sort of noise or tabulation, you are able to climb over the edge cap and come to this point. Is that okay? So that's why optimization neural network would be better than traditional digital computer. But okay, this theory have been around for many years, and this theory have been around. AI have been there for many years. Same thing for neural network. But in the year that I actually study PhD program, I graduated in 96. 95, in that year, we are using 2 micron technology, right? And then later 0.5 micron. Around that year, that's about micron. And now we are talking about 5 nanometer in TSMC. I talked about it yesterday. So from here to here, it's an order of 500 to 5. So it actually a order of 100. And if you count the silicon by one side, a factor of 100, two sides, it will be a factor of 10K. So the same area, originally you can put one transistor, right? And that transistor size been shrinking to only 1/1 10K. So the same original area, you can actually put 10K transistor in there. So your computing power grow by 10K. Okay. So in 95, maybe we put 10 neuron over there. Now we got 100,000 neuron over there. So way more powerful than what we had before. That's why you see like AI have been there for a long time, but about a year 2015, you suddenly see AI take off, right? And now everything is AI, everything is data science. And that's because the improvement of silicon. Still under the Moore rule, right? Is that okay? More slow, more low, yeah? Is that okay?
Yes.
Yeah.
So that is very important change that actually during the year actually take off. Okay, so AI right now is very important. AI right now is very important. And how are you going to study AI? And then how is AI or data science related to our programming language? That is what is key here. I'm trying to discuss. Okay, so if I teach you the traditional stuff like how this programming language related to machine, I think it's not too hard to understand. So here, let's look at how AI is related to uh, programming language. Okay, so So let's think about speech, right? Let's think about a speech. Let's think about language and speech. Okay, so basically your spoken language, say let's consider that we have Japanese, right? Okay, so you have signal processing section, right? So signal processing means that you have frequency domain stuff, whatever you talk about it, right? And then come in here, you actually do cleaning, and then you end up with a better signal by DSP, some sort of DSP, right? And compilation, so you go into a digital discrete format information, something like that, right? And then next one is actually pattern recognition. By pattern recognition, what you would get actually will be what? Text-based. So text-based will actually, you got what? RUL, right? Is that okay? And then this RUL stuff actually would be put into a file, and we do file processing, right? And read into a system, and we do tokenization. And by the tokenization, we actually put into semantic network. And then we do AI analysis, right? We translate that semantic network, and then what? We generate into a text. What kind of text? English text, right? And then we do speech synthesis. Okay, and we actually get English learner will be actually be able to know it. So here, that's the whole process of the importance in, and programming language actually starting from file processing, translation to English. This is where PL will help you. Is that okay?
Yeah.
And this is section you should see, look at it. It's more like electrical engineering. You have DSP. You need to do signal processing stuff. Okay? So that's actually is what we try to study it. Okay? So that's one thing we is very important. So some language like in English we have I love you, right? So you have subject, verb, object, right? But in Japanese it would be you would be watashi. Yeah, I got it wrong. Sorry. You would be watashi. Watashi. Let me see. Is it wrong? Watashi wa anata o suki desu. Okay. So what this one actually is subject. Okay, this one actually is object. This one actually is a verb. Okay, so the order actually totally different. So you need to put this different thing, we call it token. I is a token, love is a token, you is a token, okay? And watashi is a token, this one, each one of them, they are one token. It's okay. But you put into your network, but you actually have the syntax union, subject, object, and verb, but they may be in different order. So you need to reassemble the different order from here to here. And in order to translate it in the best way, there is optimization problem involved. And because of optimization, you need to build up data model. And based on your past data history, you do optimization based on those data. Is that okay? Is that okay?
Yeah. Yeah.
So PL actually is processing the syntax, right? processing a lot of syntax, and then you, with the help of AI, you will be able to perform these network things much better. So that's why I emphasize on natural language so far, because natural language is one of the very important field for the research of AI. And if you know Python actually has a natural language toolkit, right? So you pretty much can get Python, and there's a natural language toolkit, and this one actually is the basis. So if you took if you take AI course, this tool package, usually they use a speech as the example, right? And you learn the NL toolkit for it, and you do tokenization, stemming, wordnet, classification, tagging, parsing, semantic reasoning, rapid wrapper for the or whatever, right? You see here quite many terms is related to what? To our programming language. Is that okay? So you can think about it. Whatever you can process the language, programming language is a special language, so programming language is over here. Similar knowledge can be used for natural language. And all of these things now are actually being handled by your AI. Is that okay? Right? And we learn this in order to learn the basic stuff. Later you can move on to learn other stuff, right? And you do have a search engine. So let's look at search engine. You do information retrieval using your search engine. So you got Google, right? And you type or whatever things over here, right? It's a Google. So these are text-based. These are text-based. And you got a string, basically. You got a string. And that string being actually sent to tokenization. And then you got analyzed. And then you try to optimize it and search the internet to get a result, right? That's called data mining. You try to use that to, based on your current data set, and then you try to do mining. And that's also part of the information retrieval. So I told you this PL course actually is the center of computer science now, because it is not the hardest course. It gives you some concept, just like when you do study physics, you do conceptual physics first. And you are asked to do SAT subject physics. No calculation needed. You just learn about concept. Why I put this here, and then actually the acceleration will double. Those kind of things you learn by the conceptual model, right? But those basic things later, the physics, you will do a lot of calculus space and college physics. That would be way harder than the conceptual one. But here programming language is conceptual. And later you have information retrieval, AI, data mining, machine learning, tons of stuff, all beginning from here. That's why this course still be considered the core course for computer science. But many people think that, okay, this one is a requirement by the university. So if I don't finish this one, I'm not going to get my CS degree. Well, that is something students want to have to get the degree done, but this subject itself is very important, and it will benefit you in many ways. So let's look at the phases of compilation. Okay, so you deal with text. We talk about text processing. Okay, and text, you process it, you get speech, and you have text, and you actually process it, and the outcome will be compiled to a binary code exe file. can be processed into some sort of a bytecode, and that bytecode is run by a virtual machine. Can be processed as some other text format data, and then you send to a search engine to search for the result. So this maybe is some sort of like URL or whatever, since you grab the information and you send to the search engine and you get a different result. So nowadays the compiler design not only focus on the traditional application here to get a binary code. It may be going this way to here or going this way to here. Okay. But we still teach you the traditional compiler design. So traditional compiler design, you have 6 stages: scanner, parser, semantic analysis, and intermediate code generation, machine independent code improvement, packet code generation, machine specific code improvement. So here actually your bytecode is an intermediate code. So pretty much actually from here or from here, you get a bytecode and it's sent to virtual machine already. So that is the bytecode, and then you have a virtual machine to do it, right? So you may hear of the word just-in-time compilation. It really is talking about some stage after here. Is that okay? It's bytecode to machine code translation. Just-in-time compilation. So eventually you have the whole program being controlled by a virtual machine, and you translate your bytecode to the just-in-time compiler, and then being converted to native code. Native code means like maybe C binary or something to run it. Okay, and then that's one way. Another way is that you go from here, you do optimization of your code based on the pipeline stages in your CPU, right? So you put into some sort of risk, right? And to optimize it. Or maybe because you have bionic chips. So the text you process up to this stage, send to a neural engine to do computation, right? That's also possible. So here, beyond this point, it actually has many possibilities now. But you still need to remember a basic 6-phase compilation is very important. So pretty much you need to memorize all of the name and function of each stage. Is that okay? You still need to know about these 6 phases and need to memorize it. Any question up to here?
I'm interested in this bionic processor.
Mm-hmm.
It's
processor, yes. Go ahead.
well, is it also using the machine code to be controlled, or is it totally different and you can't control it with a regular programming language?
You mean neural processor?
Yes.
Neural processor. Let's see.
Is it something that works?
Yeah, I'll explain it. Okay, don't worry.
With a regular language, or not really?
Well, hardware actually drive the software. It's always like that. Okay, I'm sorry. I should change it. You heard of the word like first you have integer processor. Okay, and your traditional processor is only integer processor, right? And then you start to hear the word 14-point processor, and then graphic processor unit, right? And then now it's a neural processing engine, right?
Okay. Yep.
So each generation you have different processor, and our compiler try to, we do translation to make this guy work, make this guy work, make this guy work, make this guy work. So every kind of processor, they have different computing model, right? Mm-hmm. The control always is this integer processor. So you got whatever pipelining things, and then you have a control unit. CU, right? You do instruction fetch, and then you got fetch into some sort of instruction buffer, right? Whatever buffer it is, and then you send it to control unit, and control unit dispatch control signal to control your ALU, your latches, your write back stage, whatever pipeline it is, right? So you load the data, whatever this is, traditional IPU, right? Okay, that's the model, right? But if the instruction decoding is add minus subtract, I mean also multiplication for integer, right? A division is actually a special form of multiplication. So basically, you deal with this difference and you have branch, whatever. That's done by this IPU, right? No problem.
Mm-hmm.
How about if that is a big calculation of floating point? You detect certain actually instructions, say floating point multiplication instruction, right? You can just send to FPU to do it. So the data path will be different from this traditional data path. Is that okay? Is that okay?
Yeah.
Yeah, that's easy. This portion I think is easy, is understandable. Now the next thing is like, how about parallel processing in instruction level, in register transfer level? So that's the thing about here. If we have a matrix operation, right? We have A11, A12, A13, A21, A22, A23, right? Whatever.
Mm-hmm.
And multiply another metric, right? You get a third metric, right?
Mm-hmm.
Okay. What is the degree, order of magnitude, growth, complexity? It's an n cube operation. You do this, right? You do every single one, right? Each one actually has what? N by N by N, right? Is that okay?
Yeah.
So it is an n cube algorithm. Okay, that's because you do FPU or IPU, right? That if we go into the graphic processor, sorry, it actually been put into some sort of, it can be put into some sort of processing array, systolic array. So basically the hardware is totally different. So you actually load your vectors. So you load your vectors, say certain row, certain column over here, the data pass through here, the data pass through here, and they do multiplication over and sum over there. Is that okay?
Mm-hmm.
And you can parallel load the data. So one operation, you finish whatever you want to do by n cube. You just keep pumping the data this way and this way. They will cross add, so it's a multiply and add a unit over there. And you will collect the data over there. That's graphic processor. So that's why you need a separate vector processor or graphic processor. You explore the instruction level parallelism to do that. Is that okay? That's graphic processor. So it will save a lot of time if you have this kind of dedicated processor. Is that okay?
Yes, I'm. Well,
and then next one would be then how about neural processor? What's the neural processor do? So neural processor, as I say, it's used to do optimization, and optimization problem is like this, right? So most of the time you do gradient descent, some sort of gradient descent, and I told you it may have the annealing effect, right? So that's assume that it's a very simple dydx stuff. Whatever equation it is, right? So you do integral to solve it, right? So basically that's why I told you it have a capacitor over here, right? And capacitor actually you do charge and discharge, and that would be the dydx, the dq dt that would give you the charging, discharging, right? That give you the current, flow in, flow out, right?
Okay.
Right? So that portion actually help to calculate the differential equation, so that can do integration and can do differential part. And because if you do differential part, it will actually is a gradient direction, and you do optimization over there. Is that okay? And based on the neighboring information, you pass the different information to that neuron to do that. This one is analog model. Is that okay? And we convert this one to digital. That is current NPE we have. Is that okay? That's the current neural processor engine we have. So the whole NPE design is like, how can we make this whole thing faster in digital format? And same thing, your neural processing to the IPU, to the integer processing unit, will be one instruction, do integral, and you issue the command to NPE, and it will do the whole thing for you, just like your historic array or a vector processing in graphic processor. Is that okay? So basically, you invent a different processing engine based on different computing model, say integral model or differential model, and that model you have specialized hardware to process it for you.
Right.
And then yes.
So it's gonna have like additional instructions that can do all of this.
Additional instruction, yes. Additional instruction, okay. Yes. Yeah. Okay. Additional instruction, but instruction mean nothing, right? Instruction said you add 3, 5, 20, 100 processor to IPU is the same, right? To IPU itself, it's just subtle equation. You go west and go south and go north, or you turn left, turn right. That is one instruction, right?
Yeah.
But you can turn 3 left equals 1 right, right? That's a stupid way to turn, but it still be doable, right?
Yeah.
But you can just implement one more turn left. That would be faster, something like that. Same thing over here. We have a special dedicated neural processing engine, so it will perform much better in terms of what? The whole integral, we did it in one shot. If you move this computation back to the IPU using integer processor, what happened? Multiply, add, for loop, 3 level, 4 level, and then make decision. Maybe this right way is better, left way is better. You do finding the midpoint using Newton method, and then you try to minimize it, the distance, so that you approaching certain point, right?
Yeah, much more
headache in the traditional way. Doable, not doable, but well, slow, wasting time, and then cannot pour too much computation on it, right? So basically, AI is impossible. AI had been studied maybe more than 50 years so far. 1960 something, when computer come out, there are some smart people already talk about AI. But the infrastructure, the whatever computing hardware can never support it until somewhere around 2014, 15. And we start to have some useful hardware and software that can support it. So, neural processing engine, look at who is the leader right now. Who is the leader in neural processing engine? What company you have heard of it is the leader, they are doing this?
I don't know.
You don't know?
I don't know. Intel?
Intel, it is a player.
Is it NVIDIA?
Yeah, NVIDIA, yes. Intel is a player and is a follower. I cannot say it's a follower. They have independent design, but they do not take the lead. So, NVIDIA, you can think like, okay, this guy, they are doing processor, and how come deep learning have to do with that, right? Well, you get totally wrong. They are the guy actually driving us in AI. You know what I'm saying? And why they need to have deep learning and AI stuff? Because they have virtual reality. They need to optimize a lot of things. You know what I'm saying? So game design, virtual reality, whatever, they are quite many things related to their product line, related to their product line using AI. That's one company. Their processor is one of the leading company. What else you hear about AI processor other than this company? This guy, right? I talk
Never
about
heard of
it.
him.
You never heard of that? Okay. Bionic, right? A12 start to have bionic. Hey, this bionic is what? Bio, right? So it's neural network based processor.
Yeah.
That's why they use the name bionic. And they have what? You take your iPhone 10, right? What feature being added to iPhone 10? Mainly.
Is
You
that
used to
face unlock that was added?
face ID, yeah, right? And how comes A10 or older processor you only have what? The fingerprint processing.
Mhm.
Yeah, that's because the processor is okay. That's because the processor you have A13 difference. And I talked about TSMC before. Why TSMC is so important? Actually, Apple is also one of the big customer for them. They have a special GPU, CPU neural engine. You see here, right? And I just told you a moment ago, this guy still be the control unit. They send out whatever command for them to do. And you know what I'm saying? They have special instruction or whatever, connecting them to processing the whole thing. Okay? And I told you that why TSMC 5 nanometer process is so important. That's the 5 micron stuff I told you. Is a 10K more processor can be put into there. So much more neuron can be put over here.
Mhm.
So it will be way faster. If it dropped to 1 nanometer, right? A factor of 25 more, right?
Yep.
So your processing power will be way up. If the process technology come from 5 nanometer to 1 nanometer. How comes the Intel now lose their edge? Because they are still doing 10 nanometer now, 14 nanometer now. So actually it's about 2 generations behind. From 10 to 7 to 5 to 3 to 1. Each generation is about a square root of 2, about 1.5. Because these are integer, they are not exactly 5, okay? So 1.4. Actually, each generation you swing the device by half, by square root of 2. Is that okay?
Mhm. Yeah.
If you look at the ratio, it's about that. But you don't call it 7.245 generation, right? It's actually too much. Is that okay?
Yes, makes sense.
Yeah.
Yeah, thank you.
So that's what we are doing right now. Actually, try to decode things and then dispatch the job to the processor. Okay. And try to read your input, whatever Python language stuff they may need processor to do it. So processor drive the technology. That's always like that. Okay, you get a new computer that's way faster than before, right? So the first stage we do scanning. So scanning is we get some file, we actually tokenize them and put them into tokens, and this stage we call it lexical analysis, right? So this one is doing like THE is acceptable, right? But if you actually input me TH, that's wrong, right? That's not even a word, right? Or you do HE, or HE is a word, but that's a wrong word, right? You know what I'm saying? So this stage, it deals with the tokens. What is a token unit? So let's think about if we have a Java language, if A equals 3, right? B equals 4, something like that. This is a token, 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 token. Basic semantic union is called a token. We can call it ID, variable, we can call it ID, but they are operators, IDs, keywords, maybe. Is that okay?
Yes.
So a text file, .java file being scanned in to tokens. This stage, we call it lexical analysis. And to do that, we need to study deterministic finite state machine, DFA. Is that okay? It's a regular language. So in later chapter 2, we are going to discuss this. Is that okay?
Yeah.
So chapter 2, 3, 4, all talking about compiler, and we start to study the 6 phases, should be including 5, 6 phases for the compilation. And this, I do not intend to give you the whole compiler design over here. It's too much. But we try to give you a conceptual idea of what they are. Is that okay?
Yeah.
And also, if possible, I try to give you some example using Python or Java or C to demonstrate it. So the deterministic finite state machine, you can actually study it. We are going to do it in later chapter 2. Okay. So they are state input, state transition, and then they can qualify whether a token is valid or invalid. Okay. And actually, the second stage is that, okay, given token, we are going to study the syntax, right? If A equals 3, not actually okay, but if A equals 3 and is missing left parenthesis, wrong, right? Wrong. Not actually syntax analysis. Is that okay?
Yes.
So from tokens, we do next one. We have the series, a stream, a whole stream of tokens. Then the next thing we are going to do is to do syntax analysis. And here, because we need to check left, right parentheses, so this one need what? You can still use a finite state machine to solve it, okay? But that actually way too painful. So here we need to do a push down automata. And what does a push down automata have? So you can save time compared to finite state machine. I just talked about it a moment ago. What is the addition? What?
The stack?
Yes, the step. So now you have a call and return. So here you can save this one to the stack and then pop out, right? So it's better to do matchings. For example, that you may have A plus B parentheses greater than C times D plus E star, right? So that you have multiple parentheses. You will need the push down automata to help you to deal with the syntax much better. Is that okay?
Yes.
That's why this stage you need push down automata. And so that's why before the discussion, I do show you this, right? And these are very dry stuff, okay? Nobody like to study the mathematical symbols, curly braces. That actually is quite painful to study. Some of my homework actually do have that because I want you guys to learn some more formal math, and then you can go master or PhD study, or that's my original plan to put something there. But it turned out that most students at Louis are more practical, looking for coding job more. So if you want to modify the homework, you don't like the homework, you want to submit a program, I actually accept it, okay? Okay?
Okay, sure.
Some students really don't like it, okay? A lot of math symbols, whatever. So here we have push down automata. You have finite control, you have input, and you have push pop for the stacks. Okay, whatever this is. We will study this later to see how push down automata help you. Next one is semantic analysis. So we have the correct program structure. Now we are going to do semantic analysis. Semantic analysis now actually have two parts, static and dynamic. Okay, what is static? Static actually is, what is static to you if you hear the word static and dynamic when you do computer programming?
Well,
here, let me see. Anybody know it?
Well, things that are static if they don't change.
They don't change. Okay, they don't change. Good. Steady, they don't change. Yes. First impression, they don't change. That actually is the correct answer. Yeah, they don't change. Yeah. So basically, if you do Java, if you know Java, public, static, void, right? You do this a lot. What does this static mean? It actually no change. Yes, no change in terms of what? In terms of putting into a measure area, memory model. So this one static, it doesn't belong to any instance. So they will be put into the measure area. But something like you may have an integer x equals 3, right? This one, if it is an instant variable, it will not be put into the static area. It will be put into a heap. And then your object will be there, and then your x will be inside there. It will be a dynamic memory. So when we talk about static, it's no change. That's number one. It's no change or don't change. Second, sometimes it means shared property. So when you have a static integer, number of students in a student class, the state variable means it actually shared by all objects, right? It's actually shared by all objects. So when you do constant, say final static double pi equals 3.14, right? This is a constant. So every object see the same pi value. We call it static. For one thing, it actually put into the measure area. And for the other, it actually is a constant, so no change. And it also is a shared variable. This value, you can use it in object 1, in object 2, in object 3, is the same value. Is that okay?
Yes.
It won't. It is the same copy. So if you don't have final, object 1 can change it, object 2 can change it, but everybody will see the same copy. It's a shared property. So when you do number of students or the next ID variable, it is a shared property, and you increase it in object 1. Object 2 will also see it. Is that okay? But if it is a non-shared property, say you have a radius for a circle. Your circle 1 is 0.5. Your circle 2 may be 2.5. Your circle 3 may be 4.5. You update one of them, they will stay just with that object. They will not be propagating to other objects. Is that okay?
Yes.
So that's instant variable. It's not shared and it's not static. Okay? And here, static have another meaning. Here we have two meaning already. One is no change, one is shared. The third one is compile time. So usually compile time versus dynamic is actually wrong time. When you see static in computer science, most of the time it actually is compiler time versus long time. So static semantic analysis compile time. So you check, hey, I have a integer a, right, equals 3.5. Sorry, that's semantic error. Is that okay? Who will report it? Compiler will report it.
Yeah.
It won't allow you to do it. It was told you that lossy conversion from floating point to integer, right? Java compiler will report it, right? But okay, but that's semantic error. But some semantic error do being figured out at runtime. Something like a divided by 0 is a runtime error. Compiler, okay, you will let it pass. Is okay? As long as this 0 put in into somewhere that integer can be can play, it is legal. So compiler will not pick it up. But at the wrong time, you run into trouble. So the runtime error usually will not be picked up by the compiler. So say you have a student S, right? And you do not have the new student whatever stuff. So you don't have object, you only have a reference. At this time, your student actually is null, right? But later, if you did not create an object and you do s.getName, sorry, there is no getName as associated with that object. So you will see null pointer exception, right?
Yes.
And that's runtime. Compiler doesn't take it. Compiler won't check it. Is that okay? It's a runtime error. But if you do this, right? If you do this, you have student S and you assign 3 to it. Sorry, it's the wrong type. So compiler will pick this one up. Is that okay?
Yeah.
So semantic, so token is okay. Token you pass it, right? Token you pass it, and then syntax wise, okay, you follow the type and then equals and value stop. You may pass. Next one, semantic. Okay, sorry, type mismatch. Don't allow. That is semantic analysis. Is that okay?
Yes.
So we cover different stages. I try to use simple example to actually help you to understand. So, but the whole stage will be very complicated. Okay, so now we finish the syntax semantic processing. The whatever can be picked up by compiler is actually okay now. So we are about to generate intermediate form. Okay, so we do parse it. We have parsing tree. We are about to generate code, but before we generate code, we try to create intermediate form. So what is the purpose of this intermediate form? It actually is, we have a file, right? And we pass through the 3 stages we talked about so far. And we are about to generate that exe file. But we need to actually, we need to go through the instruction set, finding the right instruction for it, right? But this one may be a Mac machine, maybe a Windows machine, maybe a different kind of machine. So let's do this. Let's do machine independent optimization first. So we want to make sure that if not given any hardware information, how can we do optimization to make the code smaller? Is that okay? To make the code smaller. So maybe something like this. Maybe you have a very complicated tree, 1 + 3 parentheses times 4, and then parentheses plus 4, okay, and then plus 3, okay. And you need to push up. A lot of things you need to do. But this one, apparently, you can do 1 + 3 times 4 plus 4 plus 3. So you may get flattened and optimized somehow. So the parsing tree can be optimized. We call it the intermediate form. So we try to change the intermediate from the passing tree to intermediate for. So they open reassemble machine code for some imaginary ideal machine. Try to reassemble them. Is that okay?
Yeah.
Making sure that it doesn't have too much redundancy or overheads. Okay. Compactness, ease of optimization, making sure that before we feed into machine-dependent optimization, the thing that we can deal with without touching machine can be optimized. Is that okay?
Yes.
Okay, so let's see. Last two phase. Okay, last two phase depend. So from the point, say Java, already get out, right? It give you the A class already. So that's a bytecode. And then say, bye-bye. I actually can send my class, or I can actually compress it into a .jar file, and I'm going to send it to other people to use it, right? And it is platform independent because my virtual machine will pick up the jar file or my class file to run it. So at that point, they don't need the last two phase because the optimization being done in where? In the virtual machine, Python virtual machine, Java virtual machine. Your bytecode class file will be run on the Java virtual machine, and you actually don't see the .exe be generated, right? So that's it. But now we talk about the last two phases. It actually is about the exe file. So it will be related to C, C++, those language that is machine-dependent languages, platform-dependent language. So here, now, we need to take consideration of the optimization of your instructions. Then you need to study. This is a super pipeline machine, super scalar machine, VLIW machine. This is 4-core, this is 3-core, this is 10-core, this is a shared memory model. 4 processor, 1 memory. This is a processing unit, has its own local cache. Okay, whatever CPU it is, they are different, right? You know what I'm saying? They are different. And your way of optimization will be different. Code generation will be different. Your even same instruction set architecture based on this model and based on this model will be different, right? Is that okay?
Yes.
And which processor is the fastest PC use processor? Intel architectures processor. Which one is the most powerful one at the moment? You have an idea how many core? You may hear 4-core, 8-core, but how many core right now is the state of the art?
Aren't the AMD Ryzen processors up to like 16 or 32 cores now?
That's probably half
Like
a year, yeah, sometime before. So it actually go to 64. It's AMD C4 core 3990X 64 core. Is that okay? It's the most powerful.
Yeah,
So that's why I told you yesterday that the war between AMD and Intel. Intel is in trouble. Why? This guy still using their 10 micron technology. This one in TSMC 7 micron. It actually may be 12, 10 still shaky. So, well, a generation, it would be a square root of 2 in one side, 2 side would be double. So if this guy 32 core, it can do 64 core, right? So it will be one generation ahead of it, right? But actually no competition, right? No competition. It actually black belt to hit a red belt, so not fair anymore. It's different generation. Is that okay?
Yeah.
So CPU competition is very important, and that's why the processor is the key. So we talk about so much. Actually, it's trying to help you to understand why we study PL. It's actually try to know the compilation stages, try to know what's the relationship between programming language and machine, and then try to be able to later develop some sort of front stage compiler, or maybe interpreter, or maybe a search engine optimizer. You know what I'm saying? That's the goal. Okay. So then it will have the machine-specific optimization, target code generation, simple table. These are typical compilers terminology. And then it's the front-end compiler. So we actually right now so far talk about whole compiler and front-end. When we talk about front-end for compiler, it is up to the intermediate code. So basically, right here, right? Whatever Java compiler is, it is compiler based for Java, right? This portion Java actually had virtual machine, so it actually doing interpretation. And we call Java hybrid type, right? Hybrid type. And C double plus is compiler based, so you go all the way down to here, right? So here actually, this portion we call it front end. This portion machine dependent, we call it back end. Is okay?
Yeah.
So
and we spend more time on front end here. Okay.
Okay. So question.
Yes.
About C and C++, they don't do the intermediate form at all, or do they say
you can dump assembly, or you can dump code object code .o code, that's intermediate form. Yes, they do have it. It's called .o or .asm or .s some platform. You do see .o code, right? It's object code.
Okay, so and then they work in there.
Yeah.
Okay.
But you need to link them together to a .exe format, right? And actually, if you do Fortran can also go all the way to the .o code. And then Fortran is also the old-fashioned compiler-based language, right? So they do have a few language still have that. You need to actually compile it all the way. Okay. So now we are going to look into some simple example of how the front end is doing. So front end means a scanner, parser, semantic analysis. Okay. So here we are given a GCD program. Okay. This GCD program, C language. Okay. And some of you already submit some GCD program. So tell me what algorithm this guy use. Anybody can understand what this guy use? So basically, lexical analysis, we are required to generate different tokens like this, right? But in terms of algorithm, this guy use what? Successive deduction way. Okay.
A question for you, real quick.
Yes.
When you say a GCD program, is this greatest common denominator?
Yeah, greatest common denominator.
Okay.
Yeah, or you call it GCF, greatest common factor. Actually, the same. Is that okay?
Yeah.
Usually these two terms sometimes are mixed. So that's the thing about this. Okay, we have a equals x times f actually, and then b equals y times f, right? So when x and y prime to each other, we call this guy a GCD or GCF, right? Is that okay?
Yes.
Yeah.
So this one will work, this algorithm will work because if you look at it, a minus b would be equals x minus y times f, right? So it's still a multiple of f, right? If this one is not zero, right? Or b minus a equals y minus x is still a multiple of f, right? So we do what? Checking for the bigger one, and then the big one minus the smaller one, you get still a multiple of f. We keep doing that until two are the same. When two are the same, that is f. Is that okay?
Yes.
Yeah.
Yeah. This guy called GCD, so successive deduction. But how about, have you heard of the functions Euclid algorithm for GCD?
I haven't.
Yeah, so let's think about, we have this guy, 32, 48, right? So this guy, let's call it M. This guy, let's call it N, right? So we do division. So 1, 32, we got this one 16, right? So this one actually is what? This one actually is N 10 modular by M, right? And then this guy is M. This guy N 10 modular by M. Now we use this one actually to do 2, 32. We got 0. When this becomes 0, this guy would be the GCD or GCF. That's called Euclid algorithm. So you will see a GCD, maybe if you do computation, you have GCD of N and M, okay? And then we do if M equals 0, return N, okay? Otherwise, we return M and the N 10 modular by M. And that one actually finished this calculation. We call it Euclid algorithm. Is that okay? And just a few lines, you can do it. So let me try to use this one, write this one in Java. Okay. Sorry, I have some other students, so these are from other course. So let me create a new project. Okay. I'm sorry, not this one. I should put into CS64K. Okay, let me create a folder called Pooja over here. Okay, so let's do Pooja over here, and let me actually create something called GCD. Okay. So here, let's do this one. Let's create a program called GCD. Okay. So that's it. The Euclid algorithms like that. Okay. Then we start to do tester. Okay. So here you can see like 32 and 46, 48 GCD is 16. 48 and 32 is also 16. It doesn't matter. Why? Because if you do 48 take, 32 take modular by 48 is still 32, right? So you actually here, this one is your M, this one is your N, this one is your N take modular by M. So they will just swap because next time you will do 48 take modular by 32. They will swap. So this guy or this guy doesn't matter. Is that okay?
Yeah.
Yes.
And then 97 and 65 you got one, right? And here you have this 65 and 52. They both have 17 as a factor, right? So that's one way you do it, right? So here, as you can see, you can do recursion over here. Let's do another one. Let's actually do this one. I copy from here, right? It's a C language, but let's translate to Java, okay? So here, let's do GCD2, okay? So you don't need to get integer number. We just do integer I and integer j, okay? And here we don't need to do print it, so let's do return, okay? Yeah, copy the whole thing. Is that okay? Same, right?
Yeah. Thank you.
Yeah, same. So two methods both working. So this teach you like algorithm. Actually, you may have different kind of algorithm. Behind algorithm is what? Behind algorithm is what? What make the difference between this version and that version? You have algorithm. And then before algorithm, it will be program, right? Program before algorithm, and behind algorithm, you have math. Is that okay?
Yeah.
Oh, yeah.
Yeah. So this is the way. So that's why this is very important. Do data science, you need to learn math, and then you find algorithm, and you do program, and then you do compilation to find exe. Is that okay? To do implementation for it. Okay, that's the whole thing. If you want to specialize in computer science, that's the whole thing. And here you see it actually got tokenized. A valid computation, you prepare your own code, you actually would submit it to compiler, right? So you would do tokenization. It will be something like this. Okay, you got really every token. And after that, we do syntax analysis. So we base on context-free grammar and parsing, okay? And we do recursion for context-free grammar. Previous stage for tokenization, we do regular language to do it, okay? And then next stage, we do context-free grammar checking. So that one come with content-free grammar. It actually need to have the state. It will have the push down automata for it. Okay, and then we start to construct some sort of grammar and then pass your data over it. Is that okay? Is that okay?
Yeah.
Yes.
Thank you.
Yes. And then you pass your whole program that GCD into such a format. So you see integer, whatever, it actually generates some sort of tree like this. And then it based on this tree, they validate the program. Is that okay? So basically you finish tokenization, it will be a string of token like this. Okay? Will be something like this. And then you pass through the compiler based on the counter-free grammar, and we write this whole thing into a compiler and check in the grammar, and it will generate this sort of parsing tree, right? And this sort of parsing tree so complicated. I mean, then the syntax tree would be something like this. And then you validate it, and then you generate generate this simple table, and then generate an evaluation structure, and then you generate your intermediate code based on this syntax tree. Is that okay?
Yes.
So based on this syntax tree, you generate your code. Okay, so then next one is development of a language. Okay, so to develop a programming language, you need to have computing model. As I told you, lambda calculus, vanilla machine, logic, neuron, DNA. You come up with different computing model, right? And then you may put them into a processor engine or whatever you can have, or it may be purely a software. Then you try to come up with a programming paradigm based on the model. And then you design a language by providing the keyword type, composite type, control flow, program structure, object-oriented programming paradigms, and then generic programming, and then functional programming, whatever language structure. So for us, study programming language, we pretty much study almost the whole thing. Okay, but here this course is a introductory course, and later you study compiler design. Is that okay?
Yeah.
Quite many topics. So that's why I told you this PL course actually is the core of the computer science. Okay, anyway. Computing model, you have this memory control unit, ALU type model. This is called von Neumann machine. And I told you von Neumann is the first person put the memory into processor. So we honor him by his name, okay? And then we have neural network. We have lambda calculus, fuzzy logic. Okay, this one's and DNA computing. And you may have optical processing, and you may have mechanical processor. Okay, that's different model. And here is the principle of programming paradigms. So how to study this guy? This guy actually tells you what are the different programming paradigms. You have descriptive, declarative programming, and then first order functional programming, okay, starting from here, it branch out different things. So here, from first order functional programming, it branch out imperative programming, and it's C, C++ Java. Go all the way over here, okay? And then here you have ML or whatever. So what are these? What does this chart actually tell you? It tell you the language family. Is that okay?
Yeah.
And the relationship of the language family. How about human language? Does our human language has the language family? we have Indo-European language family, right? Indo-European language family. Let me try to find a tree. Yeah, this tree structure. So this is Indo. This is too small. I'm sorry. Let me find someone here, maybe. This is Indo-European language family. So you would have, well, Italic, okay, Celtics, okay, whatever, Germanic. English is one of the Germanic language, whatever. These are different Indo-European languages. Okay, and then you have Altaic language family. This Altaic family, you may not believe it, but actually they are in one language family. And the people actually look different in this whole Altaic family, right? Japanese, Korean, Mongolian, and these Turkish people, right? They don't look alike, right? They don't look alike.
Right.
But these are Altaic language. Okay, so these are different language. So that one actually, the one I show you actually show you the language family for computer. Same thing, they have functional language, different kind of language. And you also have one other important language is Sino-Tibetan language. And Sino-Tibetan language is basically, I think this one more representative. China, and then Burma and Tibet and this whole region. Is that okay?
Yeah.
So it's not by the country's boundary. Totally different. Okay, totally different. Some may look alike. Maybe Korean look more similar to Chinese people than the Tibetan or Burmese, right? Actually, maybe look more alike, but their language is in different family, not as you may think. Is that okay? Same thing here. We study the language; it has different family, and if you know about some language family, you may have better chance to learn other language in that same family. Say you know C, you know Java, you pick up C double plus or pick up C sharp will be much faster than you pick up say Haskell or pick up Prolog, right? Something like that. Okay, is that okay? So that is language family. Then we move on to chapter 2. I don't know how much I can do for chapter 2. I'll try my best, but I don't want to rush it. Okay. So in case that I do not finish it, I may add Monday morning to finish this portion. Okay. This is still quite important. So section 2.1, we actually jump into chapter 2. So chapter 1, we basically talk about introduction of the languages. And now we are going to look into the syntax, okay? And section 2.1, we are looking into the first part, lexical analysis, okay? Lexical analysis means the tokens. So formal language, as I told you, is a set of rules, a language designed for use in situations in which natural language is unsuitable, right? Unsuitable. So this one, you can think about it, maybe it's like computer language is one kind of formal language, okay? And it's beyond that, okay? It's beyond that. Some language like SPICE, EDIF, okay? You may not heard of these before, but they are very important. They are changing our life every day. So let's look at EDIF. This is also a This is also a formal language. Okay, so it's like electronic design interchange format. Okay, EDIF. So basically, it's used for electronic interchange. So actually, one fab can ship the design to the other. So can anybody tell me what does this language look like? What language is very much like this one?
It's a little bit like Python.
Python? No. Python, not this kind of language.
What I'm saying is this indentation looks a little bit like Python, but
All of the parentheses remind me of Lisp. I haven't coded in Lisp, but I know it has a lot of parentheses in it.
Yes, it actually is related to this. So when we have the list first and then go this EDIF, is that okay? And somehow it's used in what? In the foundries, the semiconductor processing companies. Or if you check our US company Synopsys, they have a group of people developing this. So this is not totally useless. For some application, they are. You know what I'm saying? And it's almost Lisp-like, okay? Almost Lisp-like. Is that okay? Is that okay?
yes.
So how about Spice? Spice language is used for the AC analysis, DC analysis, all the transfer function, and then it is used to simulate your semiconductor devices. Is that okay? Let me try to find some Spice program so you have some sense of what it is. Let me try to find an image maybe. This one is a Spice program. Okay. So you will look something like this. Okay. A little bit blurred. I'm sorry. It's actually too small. Let me try to find another one. Maybe this one. A little bit better. You probably can see. I don't know. I try to put it into a new tab, but it come out the same thing. Let me see. I try my best. Okay. So here you actually see right here it has some R, right? So it basically define a register from here to a certain node. So here node 10 to 15, it define a register. And then if there is a C, right? If there is a C device, it give you two nodes and it describe a network of the electronics. Is that okay? Is that okay?
Yeah.
Yeah. So anyway, that's a language to define the electronics. So language is a tool to model your design. Okay. So it's come up with a set of rules. And formal language is a collection of language which is beyond, okay, beyond natural language. It's when natural language is not suitable. We try to use it in math, in logic, in computer programming, in electronics. Is that okay? And then we have a set of rules, we have input, we have machine. These three are three in one. I talked about it before. So something like this. You have an input language. This one is the informal language, okay? It's not really formal. Informal language, you write it in this way. And then we have formal grammar. Say this one is a regular expression language. You build your state machine. So your input as a file being tokenized and then sent into the final state machine to verify it. And then you use that verification result to build a syntax tree. And then you generate Taki code. So as you can see right here, it tells you the relationship of language input, grammar, state machine, validate token tree, and Taki code. 5 different things. And these are what we are going to study. Chapter 5. Chapter 2, Chapter 3 and 4. Is that okay? and this is chapter 1. Is that okay?
Yes.
And we try to give you a whole view of how to validate the language. Okay, I cannot go too deep, but I'll try to give you something like this, a conceptual view of what the scene is. Okay, and this scene actually is the validation system for the formal language. Is that okay? And we do Chomsky grammar family. Chomsky defined 4 types of grammar in the hierarchy, of which the regular grammar classified as the most restrictive. Okay, so it actually have different family of the language, and I just teach you in a simpler way. Regular grammar is similar to finance the machine. Context-free grammar is similar to push-down automata. Is that okay? So don't get scared by these names. Actually, it's more or less like the one I show you. Finance state machine, push-down automata, and Turing machine. Is that okay? Something like it's just the name of grammar. Is that okay?
Yes.
And how important is this Chomsky? He is a very important person. So Chomsky is a very important person in computer science and also in artificial intelligence. Okay. Let me see. Check, but okay, I'm sorry. I probably cannot find it in the showtime. Okay, so that you can search for this guy. So AI starting from this kind of the grammar checking stuff. Okay, so you have the context-free grammar. It's a grammar where left-hand side of every production rule is non-terminal, and the right-hand side is any combination of terminal and non-terminal language. This is called context-free grammar, and we are going to use this one for syntax analysis. Okay, and if there is no recursion, we call it a regular language. Okay, so here let's get started for this first regular language. Let's look at this set of grammar. It's called Arabic numerals. Okay, so you have a digit. The digit can be 0, 1, 2, 3, 4 to 9, right? Non-zero digit 1 to 9. So your natural number will be a non-zero digit followed by digit with star. This star, we call it clean star or clean closure. So if you have a bar, that's called optional. Okay, so your digit can be 0 to 9, right? Your non-zero digit can be 1 to 9. So your natural number is defined as non-zero digit followed by a digit star. So we can write something like this. Basically, your natural number defined as 1 to 9 followed by 0 to 9, any number of it. So here say you may have single digits, so you go all the way to here, right? Get out. This one is say 0 to 9 star. Now actually means you can have 1, 2, 3, and you actually can go back to here, right? Many times. So it can be 1, 0, 0, 0, 0, right? So if you say that actually if you say that this is natural number, but if you want to include 0, the grammar won't be like this. If you change your 1 to 0, say I include 0 to 9, this is actually wrong, okay? If you write a grammar like this, it's actually wrong. Why? Because you may have a chance to generate 0, 0, 0, 0, 0. That is actually very grammar. If you put it like this, that's not natural number. That's not positive, non-negative number, right? If you want to write a non-negative number, the correct way to write this one is not this one. It actually is, you still keep this one 1 to 9, but you need to add another pass, just include a 0 over here. Is that okay?
Yeah, thank you.
Yeah. So this actually is the green one. I call it is like non-negative one. Non-negative number. Okay. So without the green one, just the red one, it actually is a natural number. Okay. How about integers? Integer, you may have negative sign, right? So actually you will come with nothing, or you have a negative sign, or you may have a positive sign. Come to here, right? And you would have 1 to 9 over here, or you can go 0. I'm sorry, this one is too short. Let me put it a little bit longer. But this one is actually repeated, can be have a start. When you have this clean start, it actually means 0 to infinity time. Is that okay?
Yeah.
So this one is called integer. Is that okay?
Mm-hmm. Yes.
So when we define a term, we see an integer, or we see a natural number, or we see a non-zero digit, or we see a digit. It can be described by this one called syntax diagram. Is that okay? Or SDD. Is that okay?
Yes.
So you draw this, and then you go back to look at the regular expression grammar. Okay? Regular language grammar. It will be easier to understand now. Is that okay? It will be easier to understand now. Here, this one is regular language. And this is the grammar, regular grammar. So this duo, it basically means like digit. So digit is digit by itself. Digit by itself is actually from 0, 1, down to 9. Is that okay? Different way, but only one of them, right? So this optional is actually different paths. Is that okay? In syntax diagram, it's actually different paths. Is that okay? So you take this route or this route, that's option. Okay? When we see a clean start, when we see clean start, this digit, that means this digit will go back. It's a feedback system. It is a loop. Is that okay?
Yes.
It's a loop.
Yeah.
And this one non-digit is non-zero digit is not a loop. So it's only one time over here. So basically this set of duo, this is non-zero digit, okay, non-zero digit. And this whole thing defined as a natural number, right? And I already drew the integer and the non-zero integer for you, right? So this kind of thing, we call it regular language, and you draw the syntax diagram and you can write a regular language grammar. And then we try to find a FSM to help to validate it. So your thing go into your computer, your program, you will be able to verify your grammar, right? Is that okay? And good thing about this regular language is like, before we go to content-free language, good thing about the language is like you can always find regular expression to help you, right? So you actually can try to find something that can actually help you to do regular expression checking. Is that okay? So we will actually have a chance to write this grammar in regular expression to validate it. Is that okay?
Okay.
Yeah, some.
So I think that this will take longer time when we do this regular expression. So how about Monday morning, 10 o'clock? Let me add one more session to talk about how to write regular expression.
Did you say 10 o'clock?
Is that okay?
Is that Central Time?
Central, actually 12 o'clock your Central Time, 10 o'clock my Pacific
Okay,
time.
so
Same time Monday. Let's put it that way.
Okay.
Is that
I'll be
okay?
there.
Yeah.
Yep.
So I'll try to teach you how to write starting from the syntax diagram to regular expression and how to validate it using Java. Is that okay? And then
Sounds good to me.
we will move on to the chapter 2. Okay, I don't want you guys to just listen to a lot of things like graph, grammar, mathematical symbol, and end up not going to use it, right? Is that okay?
Yes.
Okay, then sorry that I don't have time to finish it. We meet on Monday.
That's okay. I'm quarantined at home. I'm not going anywhere. I've got all the time in the world.
Same thing for me. Yeah. Okay. See you on Monday. Okay. Bye.
Okay.
All right. Thank you so
Have
much.
a good weekend.
Bye.
Bye.